This is our talk. We know that we sit in front of you guys and coffee, much like Lee's was earlier. So our talk's going to be quite photo and image-based. So hopefully it's just a nice thing on your eyes that you can hear and see what we get up to. Our talk's going to be mostly around the design, build, fly project-based teaching that we do for aerospace engineering students. The presentation is going to cover some introductions on who we are, what we do, and why we're here. Cover some educational use cases of ArduPilot through our fixed wing project, our group design projects, and then also look at some of the AutoPilot resources we use. And then we'll hopefully just discuss some of the challenges we see using ArduPilot in education for aerospace students, and hopefully get some feedback from you guys through later discussions as the conference goes on. So start off with, who are we? We are Slot & UAV, which is a research unit that does teaching, does commercial enterprise activities within the university, and also does research. And this talk is focused very much on our teaching outputs that we do at the University of Southampton.
Hi everyone, I'm Cameron. It's great to be here. So I'll quickly go over not so much the student-facing side of it, but a little bit about the aircraft that we have worked on as part of our work. So on the very left, we've got an example of our 35-kilogram, 4-meter wingspan fixed-wing aircraft known as Spotter. This has been kind of the workhorse for the last 10 years. You can see a great photo there in the bottom left. That's at Farnborough Air Show. It's just flying over the red arrows. You can see just under the right wing. We've also performed BV loss operations. The middle section shows photos of an aircraft that we named Valerie, and this was used for active volcano monitoring. So this is some video and photos from a flight that took place in Guatemala up to the summit of Volcán de Fuego, where it would perform both visual inspections of the state of the volcano. It was constantly going off when we were there, but every like 30 minutes this volcano would explode. And it was also looking at collecting ash samples to bring them back down for future analysing. As well as fixed-wing aircraft and VTOL aircraft, we also work on multi-rotor aircraft as well. You can see an example in the top right. This is P drone, or persistent drone. The idea of this drone is it's powered by, or it recharges with large solar panels, and then it can use microsensors, or it can move microsensors around an environment. The idea of it being that they're very cheap to make, and you can make loads of them and disperse sensors into the environment and reposition them. And then in the bottom right, project that was fire drone. So this was having a multi-rotor that's capable of taking a payload around 5 kilograms, developed by another university in France. And the design ethos of this aircraft was to have everything enclosed, to keep it away from smoke and heat, and as well to be used by firefighters with, say, quite thick gloves on. So everything on that is big latches, big, removable arms. So that's a little bit about the aircraft that we have in our premises. So why we're here, we want to share our experiences with you. So we're a little bit different in that we're educators, so we don't have a product to sell. We're not developers, so we do enjoy getting involved with the code base. And hopefully we can show you what we do and how that's going to shape our future teaching efforts, and hopefully have a chance to collaborate with you all. And there's already been things that we've picked up on that's really interesting that we're going to feed back into our education programs. So the students will come across us twice in their studies. The first is in their second year, where they're tasked with building a fixed-wing wing. So we provide them with a fuselage, and they go away in teams and design a wing for it. And then the second is later on in their studies, in their fourth year, where they'll do a group design project, or a GDP, where the projects are a bit bigger, a bit more money towards it. And that is where they really get involved with the ArduPilot resources and the ArduPilot software.
So to start talking about the student design, build, fly projects, we're going to start off with the fixed wing project. This is where the students in their second year are tasked to build a wing and a Arduino controlled gimbal system And their challenge is to make that wing have the largest speed range. And that's the difference between the maximum speed and the minimum speed. And they are asked to design some high lift devices on there. For the gimbal, they are making it as small and as lightweight as possible using an Arduino, and it's got to try and correct pitch and roll and keep it level. And we put a little camera system on there to get live video feedback. Finally, we limit them on materials, so we stick them to working with plywoods and the solar film covering, partially because it makes it cheaper for us to operate, but also exotic materials like carbon fiber probably will make this project a little bit too easy for them to apply their structural engineering skills at this point. And they get about 12 weeks to start from absolutely nothing to getting to the flying field and seeing their design prototype fly and see how well it performs. We test the system in a couple of stages, some of which in the lab, which we'll talk about in a second. But when we get to the flying field, we have about 3 phases of I'm going to say, semi-automated flight test. And if we ignore the takeoff and landing sections, we put them into a low-speed race course track. And this is where we set this cruise speed as unfeasibly low as possible, and we essentially test ArduPilot's stall prevention feature. We deploy the high lift devices, and we attempt to do 3 orbits of that. Depending on how windy the day is and how well they've actually made their wing to fly as slow as possible, we would maybe get less than 3. After that, we switch to a high-speed circuit, and this is where it becomes slightly semi-automated, and that's because we use the throttle nudge feature to bring the throttle up to 100%, and we've cleared up the high lift devices. And again, we try to do 3 high-speed circuits. Again, we might not manage 3 because their design might be really draggy, or the high lift devices might not have fully retracted, and therefore we've got this heavily draggy system. Following that, we do some manual handling, and this can be quite an exciting moment of the flight test, because it turns out fly-by-wire A and Auto are very good at masking trim conditions and asymmetric lifting on the wings. And so if you do have an asymmetric flap deployment or retract, when you switch to manual, the pilot has to work a little bit hard to correct that. And that's to see, we do the manual handling to see how responsive the aircraft is from a pilot's perspective. So that covers the kind of automated mission side of things. But when the students are there, we used to just put the aircraft in the sky and call out what we thought the minimum and maximum speeds were from the routes. But we've decided to kind of apply our knowledge of the ArduPilot system, and we've created a live data dashboard that is suited for the task at hand. And so on there, we have some little widgets that show the data that the students need to see. So I can try and use a mouse on here. So down here, we have the minimum speed and the maximum speed and the throttle percentage. And they are doing some live 3-second averaging based on some flight conditions. And we'll cover this a little bit later when we talk about the ArduPilot resources. So they get a live idea of how well their wing has performed. But then after that, we do some log analysis to get a true-ish reading of their minimum speed and maximum speed. And then they can compare that against their predictions. During the flight, they also have their gimbal giving a live camera feed down. The good ones, you actually can understand what's happening. The bad ones, where they've tried to implement their understanding of PID control, you might get a little bit motion sick when you're actually watching the data dashboard. But to test the gimbal, we actually do some testing inside in the lab, and Cameron's going to talk briefly about that.
Yeah, so here we have one of the gimbals on the, so we have a custom tilt table that we've made. It's basically just a swash plate that's upside down. And we can use this to put in roll and pitch perturbations. We can also apply vibration to it as well by shaking the stepper motor very quickly. So above the green section, that is where the student gimbal will be placed. You can see the red 3D printed parts. That's a mock-up that we give them. Basically, that gets swapped out by an air unit when we do the actual flight test. You'll see the vertical cylinder on the 3D printed part. That's because when we do the testing to get a quantitative value for the student's grade, we put a laser pointer into that gimbal. That points up onto a sheet of paper, and then we take a long exposure photo, 60 seconds, from top down. and then we run a simulated flight with the tilt table. Obviously, the students are watching at this point, so they get a really good visual representation of how well their system's working, how well it's going to stabilize the camera once we have it on the aircraft. And then we use computer vision to grade the individual images. And you can see on the top left a really good gimbal, so obviously that laser pointed dot's concentrated to the center, and then below it a not so good gimbal where it's gone outside of the bounding boxes and got a lower score. We also test the wing before it flies, so we do a kind of an airworthiness test. We test it in bending, so we prescribe hanging points on the wing, which are given to the students as a kind of interface document. So they have to build those into it, and then when we test their wing, we invert it, we hang it onto a frame in the center, and then at a certain span-wise distance, we hang a mass from it. And then with an inclinometer that's placed into the little box there, you can see in the top left, we can get an idea of how much the wing is bending. We then also find the flexural axis, and then we hang a mass forward of it, and we see how much it twists. So then the students have an idea of how much the wing bends and how much it twists. And then the students get graded, and we have these radar plots where they can see the different attributes of their design for their final score.
So the undergraduates, we see about 250 aerospace engineers coming through. And for us to be able to do that project, we actually only take on about 70 students. So there are other projects that the students see that we aren't involved in as much, but it might be interesting for you guys to get an idea where else ArduPilot is being used across the university in the teaching. And so one of those projects is a CubeSat project where the students are asked to create a CubeSat-sized prototype, and they place that on a low friction environment platform. So that's the section at the bottom, that kind of round disc. And they use inductive fans to make that essentially sit on an air cushion. And their challenge for this side of the project is to use reaction wheels similar to you would in space to align their CubeSat to a light source representing the sun, and that's shown in the center image. And then they also have to get it to translate on a very low friction surface to try and mimic using thrusters in space. And that system is using an Ardu rover flight controller inside. Along the similar lines to the fixed wing project, there is also a multi-rotor one in which the design brief is very similar. They have to also implement an Arduino-controlled camera, and that is to level it in pitch and roll, and then also to lock it to airframe body kind of axes. And the way this works is also to try and separate the design and structure side of things from the systems and control side of things. So we try and teach them the control architecture through small Arduino projects, which we can then place on larger projects, such as building the structure and the airframe around it. The next time we normally see students, from our perspective, is when they get into their fourth year of a master's or an integrated master's course, and it's during their group design projects, or GDPs. We see the teams that build and design UAVs, but there are a whole host of other projects that go on at the university. Their task for the UAV project is to design and build a UAV following a design brief of some description, and it's a vast array of different design briefs. And they get the full 2 semesters of their course to design it, so about 8 months, and we see a whole multitude of different platforms, designs, and things come through. The whole point of the group design projects is for them to put that theory that they've learned and where they've worked out how to design the perfect thing on paper and in a computer, and actually make it into a reality and see the real world challenges that go with that. So it's taking that theory and putting it into practice. And one of those things that they often find out is that they've got to get an Allen key or a screwdriver in to actually do a bolt up. And that's things you don't learn just by doing it on a computer. We do see a diverse array of platforms coming through. The things that we're going to show, we're going to flick through a load of photos or kind of talk through a few projects we've kind of recently dealt with. But most of those will be fixed wing designs, but we do also see a fair set of VTOLs and multi-rotors designs as well. And we give them an autopilot system to implement in there. And that has allowed the teams to kind of go through a rapid progression to seeing some mission autonomy, whereas before we would see much more kind of RC aircraft style designs. Now we're actually seeing the thoughts going into making it be able to achieve mission autonomy.
So here's some examples of other GDPs that we'll briefly talk about. So we have a blown flap aircraft on the left. So essentially it's a big EDF, and this sucks in airflow through ducts that is inside of the aircraft and for augmented lift on takeoff. So they can now look at the data between the EDF turned on and turned off and make comparisons there. And then on the right we have a precise aid delivery aircraft. So the idea is a large aircraft could drop many of these and it's going to deliver aid to a specific location. This team went for a tail sitter design and it worked really well in the hover. The transition flew around, could do waypoint missions, come back, transition back to its tail sitter configuration. For a nice precision landing. This team went above and beyond and then they went and designed a release mechanism, attached it to this Believer aircraft, and then in quite a shuttle-esque fashion we have the release there. So the Believer would invert, drop the little payload tail sitter, and then the tail sitter went and flew an auto mission, continued that, came back, landed, whilst the Believer mothership aircraft was put into a loiter or manually landed.
One of the other projects we've started to run year on, year out now is a project called the FASTER project. And the whole point of this one is to try and build up, at least at the moment, an internal competition, but potentially an external competition of trying to get an aircraft to be both efficient and fast. And so the students are tasked to carry a 1 kilo payload and a battery of a specific size, and fly a 20-kilometer route, which is 20 1-kilometer orbits, with the average speed of 10 consecutive orbits being recorded as their maximum speed. So they have to be able to fly fast for 10 kilometers, but also achieve an efficiency or a range of 20 kilometers. And we thoroughly analyze their logs, so we actually pull out every single orbit they do and check that it sticks with the rules. So they've got some constraints about how far out they can be from the prescribed 1 kilometer route. And last year, I don't know if the numbers are that clear on the screen, but last year they managed to achieve an average speed for those 10 kilometers of 43.21 meters per second. That is currently the record. Hopefully next year we'll go faster, and maybe people outside our university will start maybe looking at doing this, and we'll hopefully get some external competition going. Other projects we've seen, which kind of move slightly away from traditional fixed wing, we've seen a project looking to make a winch-lowered droid to do packaged pickup recovery. And so this one tried to implement the 6 degree of freedom motor mixing. Weren't super successful with implementing that, but that was the idea behind it. And so they would use 4 motors to translate their system, their droid, to line up with their camera recognition system, looking at the Aruco marker. And then on the right, we have a design brief which was kind of titled to get them to make a person-portable UAV. So they'd have a system where they'd take the catapult and the UAV, be able to carry that around with them, set it up and launch it. And this utilized the kind of ArduPilot launch systems. So it delayed triggering of the servos to release the tail fins, and then also delayed the motor spin up to make sure there's no fouling on the catapult. And again, for another composite image of it taking off, we have this system. And you can see that one of the tail fins is actually deploying a little bit too early on the kind of second in from the left. And that was just, I think, maybe a slight flex in the structure. But it shows that these students were then implementing delays to the ArduPilot system to kind of make full use of it.
So some other notable aircraft that we'll quickly go over. So this top left one, that was meant to be a high endurance aircraft. Though it did suffer from pitch stability, but it did achieve a high endurance, but it was with the help of a tree. And then we've got the top right, that was looking at toroidal propellers, so you can see the toroidal shape there. So they built the aircraft, but then also 3D printed these toroidal propellers and could switch them out for standard propellers and then look at the data that they got. And then the three images on the bottom there, that's like a flying lab. So they could change the aspect ratio of the wing, change the dihedral angle. You can see the image on the right, it's got the wingtips compared to the other two, and it could also change its static margin. Students were making use of the Lewis scripting there to change parameters based on the configuration of the aircraft.
And so what links all those projects is the systems inside, really, and that's where we've started to adapt our kind of ArduPilot resources. And the purpose is to try and support the students with hardware, guidance, and advice. And so our ArduPilot resources we've kind of been building over the years are ArduPilot starter kits, online guidance documents, the live data dashboard we briefly shown earlier, and also in-person advice sessions.
So the kits are great because they're common parts to every team, so they can talk to each other and kind of share knowledge in that way. So that's quite advantageous. Also, the kits are sponsored by Boeing, so the budget can go towards, well, they don't have to pay for the essentials that are going to have to go into the aircraft. So their budget, or they can budget for their design of their aircraft. And also we find that this kit and the items in it that I'm sure we're all very familiar with, will basically cover any system that they want to build. The only times that we might have to change out the equipment is if they're building something that is quite small and these parts are too large or too heavy.
And by implementing or kind of allowing them to use common components, we've then started to create our own online guidance documents to give that common support to those common components. And this kind of acts as the simplified documentation of the questions that most students ask us about configuring the systems we give them. But it always links back to the ArduPilot resources and the APDevConf2025 docs as well. And it becomes a useful kind of starting point to getting the students to understand the features that are available for the students. The other thing we've started to implement, we spoke briefly about it earlier, is that live data dashboard. And this was to tailor the information that the students would see on a big TV screen at the flight line with information they needed to see to compare it against their predictions, but also to compare about the other teams flying on the same day. And so we would build it so that it did the 3-second averaging based on the altitude, making sure they're not climbing too much or descending too much, and a different flight mode, and that will get shown under the airspeed. We'd give them a bit of information about the wind speed in the map overlay, and also give the live stream of the video so they can see how their gimbal is performing. The application itself is using the WebSockets connection to Mission Planner, and thanks to Peter Hall for pointing that one out that it exists. It was originally on the TCP. And then it's running an Electron app that has an Express server backend, and is then using an Angular framework dashboard at the front. And it became a really useful resource for students to see what was going on their flight day, rather than just watching an aircraft fly around and hoping that somebody was reading out the airspeed correctly. We also give in-person advice sessions to the students, and this is normally tailored around the design of the system, but it's increasingly, as they want to improve the complexity of their system in terms of functionality, it's increasingly going towards more how do we configure the ArduPilot system. And so we try and promote those tools, such as the web tools and the documentation, for them to kind of get that future independent resolution of their problems.
So kind of challenges that we face from the kind of situation that we're in, where we have lots of teams, let's say on a flight day. So as an example, radio interference. So every team has those 868 modules. And we have systematic and physical ways to try and make sure that only one team is powered on at the same time. We also want people to work on the aircraft in the pits as well. So it'd be really good to hear from people if you have any, clean, slick solutions that we could have so that we, switch to one live pair and allow for, low power comms to happen in the background, or to think outside the box in some other way. The other thing is the initial setup and documentation. So there's obviously loads of documentation out there, and that's absolutely fantastic. However, we often find that students feel quite overwhelmed with kind of what is out there, and that's why we've tried to slim down the documentation to our own kind of internal wiki, but obviously using what's out there as well. But we don't want to kind of double up on the workload there, so we'd love to have a discussion about that kind of stuff. And then students and gotchas. So this is more from like I guess a safety perspective. We're giving quite complex systems to students. So we're getting students to build really quite complex systems, and we are ultimately responsible for their safety on these flight days. So often we can see weird permutations of parameters that would result in maybe an accident for the aircraft. For example, we had one where a disarm channel or a disarm command was set to the throttle channel. It was only in a high power state that it would disarm the aircraft. It was only because we were taking off from long grass that we could find that out. And we didn't know why for a little while, and then we debugged and we found the reason why. So it's not always as simple as checking that they've got the arming checks on, which, believe me, every student turns off. And we also want to know what is missing from graduates. So there's a lot of commercial companies, or people here are dealing with commercial companies and the hiring of people fresh out of university or not university. And what is missing from graduates? What can we tailor our courses to kind of give them the knowledge? How can we improve our teaching, essentially?
And finally, we just want to close with kind of saying there are opportunities. So every one of those group design projects has to have a design brief behind it. And us, kind of on the academic side of things, produce quite a few of those. But we also get links to industry and companies to produce design briefs. So if there's anything you'd like to see tested by students, then let us know. We'd love to collaborate. We'd love to kind of work together on some of these ideas. And that also unlocks kind of access to a lot of the university facilities. We've got wind tunnels, anechoic chambers, we've got all sorts of things. And so you could get involved in some of these student projects, and that could lead on to future research for both yourselves and kind of the university. So thank you for listening. Any questions?
What an amazing course. Can I?
Absolutely.
Do we have any questions for guys?
Yeah, I echo what Matt said. That'd be great to have these days. Have you investigated the IMechE UAS challenge? Because that seems very similar to some of the stuff you've been doing there.
Yeah, so we used to attend, I think 2016 was maybe the first year, and we attended that several times throughout those years. We kind of dropped off that a little bit. I'm not too sure why. Recently, we started to pick up on going back to that, and hopefully this year we'll get another one going through to the UAS challenge. Yeah, absolutely.
Yes, hi there. I really liked your tail seater configuration, and I was just wondering, does the front wings also have some form of ailerons?
Yep, so the tail sitter has an all-moving canard on that system. So that was doing essentially their elevator control.
Oh, okay, fine. Thank you.
Yeah.
When you guys are doing the flying with various wings or platforms, do the students ever do any of the tuning aspects, or are you generally using the stock tunes?
For all the plane projects, normally it starts off stock tune, and we get about 6 full-day opportunities for students to attend a flight day, and that will cover probably about 7, 8 to 10 teams. So depending on their state of readiness, they have an opportunity to tune on those days, and then they've got 6 opportunities to get it tuned and then get the data they want. So depending on how productive, ready the teams are, depends on the state of the tune. But normally for the planes, start off on the stock tune and potentially tune it. The copters, of course, are slightly different, and they're going to go through the initial tuning setups.
Have you ever seen any disasters from bad tunes?
We have seen a few student projects that do end up in trees and in fields, normally due to kind of the design, the manufacturing of the drone itself, so they haven't quite considered the structural loads in some parts.
Cheers. Thank you.
Hi. I saw in a few pictures angle of attack or angle of side slip sensors. Is this something you build a lot? We do need more of those in general.
So I think that might have been about the flying lab one you might have seen it in. So on this one at the bottom. So yeah, this team was really impressive in the sense that they took all their aerospace knowledge from their 3 years of their undergraduate to their 4th year, and they made a flying lab that looked at aspect ratio, they looked at airspeed, they looked at angle of attack, side slip, they looked at the CFG position, all in their different flight tests. I think these are just Arduino potentiometers that they've put themselves together and then done their own data logging from. So I can't, and this was a couple of years ago, so I can't comment on the state of that. But we do see students putting together a lot of Arduino-based data logging because they want to just do rapid development of something that they are familiar with because they get taught Arduino systems throughout their undergraduate. So yeah.
Okay, a round of applause, please.